Hey, good afternoon. It's Professor Lemieux, and as promised today in class, today's video capture is on the derivation of the momentum theorem. So there shouldn't be a whole lot of mystery about this one. It's going to be very similar to the one about conservation of mass, and let's have a go at it. We're going to start one more time with the Reynolds transport theorem. And in general form, the Reynolds transform theorem tells us that ddt of some extensive system property B is equal to ddt of the same extensive property of the control volume, which can be calculated by integrating the intensive property little b times rho times dV over the entire volume, plus the flux of B through the surface of the control volume. Okay, so this is just recapping what we know. B is an extensive property. Little b is big B divided by M. And off we go. So I'm going to start actually by looking, so this is the general form. I'm going to start actually by doing the derivation in the forms that we have been using mostly with conservation of mass, which is RTT number 1 and then number 2. Right, the RTT number 1 for the very same thing told us that ddt of B cis is equal to ddt of rho little b dV minus rho V A times little b going in plus rho V A times little b going out. If I have one in, one out, properties are uniform at the inlet and outlet, and 3, that the velocity is normal, perpendicular to inlet and outlet. Alright, so really kind of what we were looking at here was some sort of a pipe, if you will, or a control volume that looks like this, where there's no mass transferred along the line of flow like that. And I'm looking at a plug of liquid or fluid, gas, doesn't matter, and it's moving into my control volume at state 1 and moving out of my control volume at state 2. So I can look at that system, which satisfies my 3 conditions for Reynolds transport theorem version 1, the restricted form, and apply to conservation of momentum if I let B, my extensive property, be equal to the mass times the velocity. Mass times velocity. So that's the linear momentum of the system. Okay, and of course if I'm looking at BV inside this control volume, so it would be linear momentum of the control volume. So what do I know about this? Well, then ddt of B cis, if this is for the system here, is equal to ddt of m times the velocity of that system, and the rate of change of momentum of the system, we know, is equal to the sum of the forces acting on the system. Right, so everything is system based right now, and that is our old, well-known Newton's second law. Okay, so Newton's second law is where we start. What we're going to do, of course, is apply our RTT both in initially the restricted form. Then we're going to consider what happens when we have more than one inlet, one outlet for RTT number 2. And finally, we'll express the RTT in the general form and apply it to this system. Okay, so what we've got, very simply put, is B sys, or B, is equal to M times V, as I got up there, which means that little b is equal to big B over M is equal to mv over m is equal to the velocity only. And now I'm in good shape to substitute that in my RTT1 form right over here and get that d dt of m times v of my system must be equal to d dt of the integral over the control volume of rho times b, rho times little b, rho times the velocity dv minus the momentum that goes in, which is rho times v times a times little b, which is itself v. Okay, so actually this is the mass flow rate, so it's not a vector. Sorry, this first term is not a vector. And this is of what actually goes into the control volume, plus rho v a times v of what goes out of the system. What goes out of the system. You notice that this term right there and it is equal to m dot into the control volume. Similarly, this term right there is equal to m dot going out of the control volume. They're not necessarily the same in this case, because we could have accumulation in the control volume. In other words, they are the same only if the flow is steady, and in the conservation of mass equation, the unsteady term is equal to 0. But that's not necessarily the case in general, so we have to track him down separately. Okay, so that's what the system is equal to. The rate of change of momentum of the system is equal to in terms of the control volume. I'm going to write it in one more form here. Rho times v. I'm keeping v as a vector because I don't really know exactly which direction this is happening. You know, could be the x-axis, could be the y-axis, etc. But what matters though is that I have only one direction. Well, that I have only one inlet and one outlet, and that they'll be aligned for me to be able to write them in this direction. So rho va. Oops, sorry, I don't want to do this. M dot in times v in plus m dot out times v out. Oops, v out. Right. So this is going to be equal to the net sum of the forces. The net sum of the forces. And voila, RTT number 1. And F is a vector here. RTT number 1 for conservation of momentum. Conservation of linear momentum with the caveats that we have A, 1 in, 1 out. B, uniform properties at inlet and outlet. And 3, C finally, velocity is normal to the inlet outlet. All right. I just want to highlight a fact here that may not be completely obvious. The fact that we're dealing with a vector equation here, that there's 3 components to this equation. One, we're talking about the sum of the force in the x direction, the velocity in the x direction. 2, the sum of the forces in the y direction, same thing, velocity in the y direction. And then finally, the third one, the sum of the force in the z direction, velocity in x, and z, in z, and in z. This could become important if I had, for example, a control volume that looked like this. Say I got some pipe that makes a right angle. Okay, and I'm looking at the flow coming into this pipe at section 1. Does some kind of a turn in the pipe and comes out at section 2, V2. What this equation is telling us right here is that the sum of the forces in the x direction is going to be equal to d dt, the unsteady term, of rho Vx over the volume, minus what comes in, and what comes in is in the x direction only, so I'm going to have m dot in times V1, plus what goes out, which is m dot out, certain value. However, V out in the x direction, V2 of x, is 0. So this term falls right out, and I'm just left with this equation for the sum of the forces in the x direction. Similarly, the sum of the forces in the y direction would give me another equation completely altogether. Now I'm looking at the velocity in the y direction inside this control volume, integrated inside this control volume, minus m dot in times V1 in the y direction, which is 0 because V1 is exactly aligned with the x-axis, plus m dot out times V2 in the y direction. Okay, so in this little 2D diagram, of course, there's no z, there's no velocity in the z component, but you know, I could write the equation in that form as well. Okay, RTT number 1. RTT number 2 for momentum equation. 2. In this case, we have more than one inlet, one outlet. Same thing as before. I'm just going to sum them all up. Right, this is 1, 2, 3. I'm still normal to each of the surfaces in which I'm going in. V1, V2, V3, V4, V5, and I will have the rate of change of momentum. Okay, so in the RTT form number 2, we're looking at the rate of change of the momentum over the control volume. Over the system. So over the system volume. So this is just B sys is equal to the rate of change of the integral over the control volume of the same thing minus the sum of the momentum going in all over all of the inlets plus the sum of the momentum going out over all of the outlets. if I have two inlets, then I would be adding the momentum at each one of those inlets, and I would subtract it from the unsteady term. That would be my flux of momentum in. And if I had four outlets, I would simply add the momentum of the flow leaving each of those outlets, and add that to the unsteady momentum term, and that is again equal to the sum of the forces in vector form acting on the control volume. Finally, at last, the general form of RTT. Well, which we have, let's see, where is it? Right here. If I have a control volume of arbitrary shape, let me just bring that guy down so I don't rewrite it. Oops, that was not pretty, but we'll be all right. There we are. Okay, so the general form. Okay, so if I have a system and control volume of arbitrary shape, here's my control volume in space at time equals 0. It matches with my system, remember, and if an element of the surface of that little control volume as an outward normal equals to n, then really what I'm interested in is the relative direction of the flow of fluid with respect to that small little element of surface. And we saw in class that the component of V that's normal to that is simply given to us as the dot product of V with n. And that's really what I'm going to be integrating over my entire surface of this entire control volume out here. And the signs, whether it's positive or negative, will align themselves, will correct themselves, whether the flow is in or out, because in the case, for example, that I drew up here where the flow is outward, we see how the value of this dot product is going to be the magnitude of the vector v, which is just the speed, times the magnitude of the vector n, which is just 1 because it's a unit vector, times the cosine of the angle between them, which is going to be positive because they're both aligned in the same direction. However, if the velocity was going into the control volume, and I had something like that, right? If this was an inlet, then we see that in this case, the angle between them is clearly more than 90 degrees, more than 90 degrees. So therefore, in this particular case, when we have an inlet, this is for the case where we have an outlet, outflow, it's still going to be equal to the magnitude of V times the magnitude of n, which is 1. And now the cosine of an angle that's greater than 90 degrees, this term is going to be negative. And that, of course, is why when we have the single outlet or multiple inlet and outlet form of RTT, the stuff that goes in has a minus sign in front of it, and the stuff that goes out has a positive sign in front of it. So substituting for B cis in our new setup right now, which is equal to the mass times the velocity, we therefore have ddt of m times v for the system is equal to ddt, the integral over the control volume of rho times the velocity over the volume. This integral represents the momentum inside the CV, which of course is a vector, plus the integral of all these guys over here over the entire surface, which is going to be the integral over the control surface, which represents the flux of momentum in the control volume. Rho v, a vector again, times v dot n, a scalar, times dA. General form of conservation of momentum. We also call that guy, oops, actually sorry, it's not quite the final form there. All this of course is equal to the sum of the forces on the CV slash system. Okay. This is the form of conservation of momentum that we refer to as the momentum theorem. And it is the general form. Okay, that's it. Just about 20 minutes, I think, is what we got here. Hope you got something out of it, and I look forward to using this as an example in class with you. Thank you.